Okay, this week we're going to talk about some really important stuff concerning the diversity of nature, and this is a really interesting part of the course because it gets into a little more things beyond just chemistry, which why I like it. But you know, we talked a little bit before about not being able to duplicate these essential oils. Why can't men in a lab recreate these oils? And this is going to answer a lot of that. It's not because, you know, there's some kind of life force in the oil, or it's some kind of, you know, spiritual thing about, or some kind of, you know, hocus pocus or magic. There's real reasons, scientific reasons, is why we can't do this, and a lot of it has to do with why I've spent so much time with you all on recognizing chiral carbons and enantiomers and things like that. It's going to be important for you as you go on in your field of medical research or biochemistry or whatever you choose to do in the field. It's a very important topic, so that's why I'm spending a lot of time on it. So first I wanted to talk a little bit about the history. Well, first I want to say many times the components isolated from nature will differ in odor and properties from the same component made in the laboratory because the natural system has tight control over the enantiomeric ratio of the molecules that it produces. So in nature, most of the time it's very specific. When there is a choice of an enantiomer, when a plant is making a molecule, it almost always overwhelmingly chooses one over the other. So, for example, in the peppermint there's like 99+% L-menthol. In spearmint, it's 99% L-carvone, you know, that kind of thing. And when we make things synthetically in a laboratory, a lot of times the synthetic routes that we use to get to the end point does not allow for any specificity on which enantiomer will form. So most of the time when you make a molecule that has chirality, you're going to get a 50-50 mixture of the L and D in the synthetic process. Now that's significant because the L interacts with your system a lot differently than D in many cases because of the whole hand and glove type phenomenon, the way things work in biological systems. And I think we have an example. Sherry brought an example for us of, let's see what we have here. Do we have the L-carvone, and do we have the D-carvone? I have to bring D because we have L in our kit. So you didn't? What about L-menthol? Oh, D-menthol, sorry. You brought menthol crystals from Arvensis. That's L-menthol. Well, maybe we don't have that, so never mind. Maybe you labeled this wrong, because I think you labeled this wrong. This is D-carvone. I don't want to mess you up. Anyway, the L-carvone is the odor of spearmint. The D-carvone is the odor of dill. If we had the sample of menthol that I wanted to show you, I would have been able to show you that it has almost no odor. But I thought we had it. I'll try to bring it next week. So how did people discover this? I think it's kind of an interesting story. And when we go back to Jean-Baptiste Biot, in 1815, was a French physicist who was investigating plane polarized light. He found that when he passed light through a polarizer, and then through solutions of camphor or sugar, the plane of light polarization was rotated. Okay, so don't ask me why a person decides all of a sudden, hey, I think I'll just pass plain polarized light through this and see what happens. When you know nothing about three-dimensional structures of molecules or anything else, it's kind of interesting that back then he would have done that, but this is what real scientists do. So you notice that some of these things rotated light to the left, some rotated light to the right, and he called the ones that rotated to the right dextro-rotatory. Make sure you get that dextro-rotatory, the full syllables in there, and then levo-rotatory, and that's really misspelled. Should be an A in there, levo-rotatory. So after that, Pasteur comes along, knowing that this phenomenon exists where this plane polarized light can rotate differently in different solutions, and so he has that in the back of his mind, and he studied crystallography, and he noticed that when he recrystallized the salts of tartaric acid, which is found in wine, that there were two kinds of crystals. And so he could look at these things with a magnifying glass and see that they were actually mirror images of one another, just like these pictures of these molecules that we're drawing are mirror images, and you can't superimpose one crystal on the other, but they look like a mirror image of one another. So he kind of saw, hey, something strange is going on here. So what he did then, now imagine doing this. You have a pile of crystals. These are tiny crystals, and you have this pile, and you physically go in and you separate all the different crystals in two different piles, and then you make solutions of each one, and then knowing that we got some of this stuff going on from previous experiments where you can get different rotations, he decides to do that experiment with the two different solutions and found that one rotated light to the exact same degree but in an opposite direction as the other solution. So it's an understatement to say Pasteur was far ahead of his time, because structural theory has not even been presented by Kekule yet. Okay, so he had to. It's not like we know this stuff, and so it's easy for us to understand it, but just think about it back then, trying to figure out what's going on here. And when he spoke of these, he said, it cannot be a subject of doubt that in dextrotartaric acid there exists an asymmetric arrangement having non-superimposable image. It is not less certain that the atoms of the levo acid possess precisely the inverse asymmetric arrangement. So he understood, even before it was even presented in the structure of all these things, he understood that there's something fundamentally asymmetric in the atomic arrangement of these atoms in these molecules. That's what real scientists do. Now, what does this mean chemically? Okay, and we've been working on this all semester long, and basically when you boil it all down, when you're looking for these chiral centers, you have to look for carbon molecules that have 4 different substituents, and to know if it has 4 different substituents, you have to rule out anything that's double bound, and if the molecule has a plane of symmetry or an axis of symmetry, you can rule out any kind of chirality. All right, so I've kind of put this graphic up here, show those would be examples of some generic amino acids, and showing a left-hand version and a right-hand version, and showing that they're mirror images of one another. And then when we try to rotate that right hand over to the left side, we see we can't superimpose it. Same thing with the molecules there. We can't superimpose those two molecules. So even though they are chemically behave the same, in other words, they would react the same way, they would boil at the same boiling point, they'd have the same freezing point, All their physical characteristics would be exactly the same except for the way they rotate light. Now, these are completely different molecules. Even though their physical properties are all the same, they differ in their optical rotation, and because of that difference, they are physically different molecules. And I've basically just explained everything I said there, but the importance of this in biological systems is one enantiomer is usually the active one, and the other one may be totally inactive, or it could even be lethal if it's the wrong one. Right? If we think of the case of amino acids, right? And this would make you think a little bit. Every amino acid in every living system of every organism on Earth is the L form, right? Why that is? There's probably a million different theories as to why that might be, but you can also have a D form, and when you buy synthetic amino acids like supplements, there have been cases where, because the synthetically made amino acid was a 50-50 mixture of L and D, I think there's been cases of where people have actually died because of that. Was it a tryptophan or something? Pardon?
D-lysine.
Was it lysine? I thought it was tryptophan. Anyway, yeah. So this is how important chirality and symmetry is in nature and chemistry and to living systems. And I wanted to go over, now this is just a simple one molecule example. Now let's bring this up to a case that's actually relevant to essential oils. And let's look at menthol. So there's menthol. There is our basic two-dimensional skeletal structure, right? I'm not showing any spatial arrangement of any atoms. It's just a flat two-dimensional structure. So if you look at that, the chemist can look at that immediately and say, oh, I've got 3 chiral atoms here. Here, here, and here. Because on each one of those, I've got 4 different substituents. None of those other positions would have 4 different substituents. If you can't see why any of those 3 has 4 different substituents, now would be a good time to raise your hand and ask me to point it out. If you cannot see why there are no other asterisk points there, now would be a good time to raise your hand and let me know. Anybody, because this is important. What are the results of having 3 different asymmetric centers on one molecule? Well, if you go through all the stuff like we just did on that bonus problem, for one asymmetric center, if you go through all that, what you find is we'll go through and we'll assign an R or an S configuration. Remember, there's a systematic way of assigning either an R or an S configuration to any asymmetric carbon atom. And that's based upon assigning priorities by viewing a molecule with a hydrogen in back and the other 3 constituents coming out at you. I'm not going to go through that. But the result of that is you can have a case where each of those 3 centers is either R or S. That results in a total of 8 different isomers just for menthol. And all 8 of these are in peppermint oil. The major one is this one, L-menthol. That is the predominant one. But all of these are present. And you have menthol, isomenthol, neomenthol, and neo-isomenthol. And then you have the mirror image of each one of these. Now imagine if you were trying to reconstruct a synthetic peppermint oil and make it identical to nature in odor and flavor and biological activity. You would have to, first of all, GC this thing and and do it on a chiral column and separate out each one of these and get its exact percentage, which is in itself almost impossible to do because there's always error in a GC. So you're not going to even be able to get the exact percentage, but get some kind of estimate. And the lower that component is present, the harder it is to get the accurate number. Some of these are very low concentration. And then kind of reconstruct all of these back up to the exact percentages of each enantiomer. And that's just one molecule out of maybe 100 that are present at 0.1% or more. And then how many of those have one chiral center, maybe two chiral centers, maybe three, like this one. And then you can see how this thing blows up in complexity and how difficult it would be to reconstruct one of these things. This is why natural essential oils aren't going to be going away anytime soon. If we could synthetically replace them, we would have done it by now. And I don't know that we'll ever be able to because it's just too big of a problem. Any questions over that before I go further with this? No? Well, this is, this goes beyond, I mean, like we talked about before with the enantiomers of the amino acids, What is going on here with all these systems? Why are they so specific in what they do? Why does every organism have an L amino acid and no D? And there's a lot of things that could be derived from that. It's hard to imagine a chance of happening of that. Some people will try to say that it could happen by chance. I don't see that, but I don't know. I think there's just a lot that we don't know that to rule out anything would be non-scientific. But yeah, the problem blows up so fast. If you've taken, who's in quantum mechanics? Anybody in here in quantum mechanics? Have they solved anything beyond just the hydrogen atom yet? In terms of the exact solution? Yeah.
We have the equation.
When you do the H psi equals E psi, and there's a hydrogen atom is a situation of one proton, one electron, right? And when I was in school, at that point in time, that was the only system in which we had an exact solution to the wave function. The only one. As soon as you introduce helium and you introduce that second electron, that electron-electron interaction term blows that problem up, and you have to make approximations, and we can never get, without making the approximations, there was no exact solution yet available. And I don't know if that's changed. I don't think it has, but if it has, let me know. But that just tells you how fast things get out of hand in nature, and trying to understand all this stuff in any kind of exact way. This is all, and these models that we're throwing up here, they're all based on approximations. Right? All we're doing is applied physics, where we've made a bunch of approximations to show little models of molecules. Whether or not this is anything in the truth is another, we don't really know.
So if you found a way to synthesize that in the lab, and it didn't really select for any particular form, that all those present at 12.5%?
No.
This one here.
Well, you see, probably, for example, if you proposed a way to synthesize menthol, which is this pair, your route would probably lead you to a product that would give you 50% of each of these. You'd probably have a different synthetic route to get to isomenthol, or you may have a route that gets you these two. But I doubt there'd be any one route that would yield all four of these. Okay? Yeah. But in each route that you were trying to do one of these, you'd probably end up with a 50-50 mixture. Unless you design some kind of chiral synthetic method that would fix precursors in a certain orientation that would allow for only one approach of a reagent to one side of a molecule to give you one product. You know, and that stuff is possible. You know, that is done. But, you know, like I said, this is all just, you know, this is applied this is applied applied physics. The chemistry is applied physics. Physics is applied mathematics. So we all are debt of gratitude to the mathematician, first and foremost, I guess. And then biology, of course, is applied chemistry. Any biologists in here? I don't want to offend anybody. But, yeah. So again, 8 total stereoisomers just for the menthol molecule, each having, that's another important thing. Each one of these has a different odor and a different biological activity. Not only just each one of the 4, but each one of these with its enantiomer would all have different odors. Okay. Any questions on any of that? So I don't expect anyone to miss any more questions of find the chiral center anymore, right? That won't happen again. All right. Now I want to talk a little bit about GC. Which the hell we got? Okay. Because we will be doing some GC analysis later. You won't be physically using the instrument, most of you, but you will be getting a printout of an unknown from a GC, and it'll be breaking down the percentages of the components of that unknown, and from those percentages, we're going to try to reconstruct the formula of that unknown. What oils are in that unknown and at what percent. This is what a perfumer does, or this is what a flavorist does. And these guys, as you might imagine, get paid a lot of money to do that because there aren't a lot of them around. And it's not easy work. Your systems will be fairly simple because we're only going to be dealing with, you know, the one. I'm going to pick one oil from each group and add it to a mixture. What do we have there? We've got mint oils, citrus oils, floral oils, herb and spice oils, leaf and conifer oils, resin and wood. 1, 2, 3, 4, 5, 6. So there'll be 6 different oils, let's say, in that unknown. And based on the percentages of the components, we're going to figure out what oil's in there at what percent. And it's just like detective work is what it is. I mean, knowing, you have some knowns, you have some known information about these different oils, and from that, and when you have oils that have components that overlap, that's when it gets tricky. That's when your knowledge of the further components in the essential oils becomes essential, no pun intended. But imagine now, and this is what a perfumer does, and what an essential oil chemist or a fragrance chemist would do, if we just didn't have those oils to deal with. But now we've got 300, 400 different essential oils to deal with, plus about 2,000, 3,000 aroma chemicals that we're dealing with. Then it's a really big problem. But that's where the nose really helps narrow a lot of things down. So usually the fragrance chemist or the essential oil chemist or the flavor chemist would work hand in hand with a perfumer or flavorist, who are not the perfumer is not necessarily a chemist. It used to be, it's changing. When I was in the business, I was a rare person who did the job of a perfumer and who also actually had a chemistry degree, an advanced chemistry degree. At most, usually they might have a BA, but very few. It's changing, like I said, but in my day, almost none of the perfumers had chemistry degrees. They were artistes. They were there for their nose, and they had very limited chemical knowledge, so they would work hand in hand with the chemist. The chemist may not have enough, be able to smell, stinky socks. They work together. He was responsible for the analytical portion. The perfumer was responsible for the odor portion, and between the two of them, they could knock out a reasonably good duplication. But nowadays, more and more. Pardon? Does that mean what?
We compare it.
I'm thinking about maybe doing that. Maybe having you group up into groups for that part. But nowadays, if there's more chemists who are becoming perfumers, and if you are one of those people who has the degree in the background in chemistry, it's only going to enhance your ability as a perfumer, because now you don't have to rely on the chemist. You have that knowledge yourself. And if you have a PhD in chemistry or even a master's, and you're also a perfumer, I can tell you're going to command a pretty high price. And if you get if you get some formulas into some big name products, then your stock goes way up. Let's see. Okay, so where are we going with this? GC. How does it work? Has everyone in here used the GC at some point? Okay, so we're just going to basically refresh the basics. What do we have? We have basically just an oven, right? Just basically a simple oven with a long, thin capillary column inside. Okay, this is a very basic drawing.
Most visual aids.
And a lot of times the inlet would be, say here, your injection. And it could have an auto sampler like what we have upstairs. Say an auto sampler up here, a robotic arm that would basically do all your injections for you. Makes it nice. So all you do is make up the little vials. You can make up 12 of them, and sometimes 100 of them at a time, pop them in there, enter all the data in the computer, and then say go, and it just will go continuously. So it injects the sample into the inlet, and it goes through this long column, which is typically 30 to 60 meters long. And this column could sometimes be a polar column, sometimes it'd be a non-polar column, depending on what you're doing. But the molecules that are in your solution will stick to this column to different degrees. Different molecules have different, what we call retention times on that column. So after they've gone through this very long phase, each one, by the time they get to the end, is coming off pretty much in pure form, right? So as these things come off, they hit what's called the MS, or the Mass Spec. Okay? So each peak that you see coming off now, what you have is, when nothing's coming off, the recorder would show nothing but a baseline. And then all of a sudden, when a molecule comes off at the end, you see a peak. And that peak represents a pure component. And basically we're graphing the intensity of the signal versus time. This is time here. Time versus intensity. Or you could say counts of carbon atoms if you're doing FID, or it depends on if you're doing FID or mass spec, but signal we'll just say versus time. So when this peak comes off, it's essentially a pure component. That pure component is then shot into the mass spec. Okay? And the mass spec is basically bombards that pure component. It's an electron beam that bombards that pure component, blasts it into fragments, right? And those mass fragments are then recorded. So this peak would then, every individual peak would have its own characteristic mass spec. And so the mass spec is just a measure of these mass fragments in different percentages. So depending on how that molecule fragments, certain fragments are more probable than others, depending on the structure of the molecule and whatnot. And so every molecule has its own characteristic fragmentation pattern, or what we call the fingerprint, the mass spectrum that we call a fingerprint of that molecule. And then this, remember, is hooked up to a computer. And the computer then has a library built into it with all these mass spec that have been recorded over a number of years. Some of them are in like government databases, the NIST and things like that. There's commercial databases that you can buy. Usually they're pretty expensive. Some of these databases can be up to like $4,000 or $5,000. The Wiley database is the one that's popular that has about 275,000 components in it. They're just mass spectra collected in a library, so that when these mass spectra come off and hit the computer searches that library and then matches it up with the fragmentation pattern, says, boom, this is what it is, and the probability that I'm right is some number, and there's going to be some number. Usually it's like 99, 98, or 90 plus. Anything in the 90 plus, you're pretty confident that's what it is. When you get down there and you see something that maybe is 60, 50, 70 something, then you're like, I'm not sure about that. And usually the reason it's that way is because either the molecule is truly something novel that we don't have a mass spec on, at least in our computer, or more likely is we have peaks that maybe are something like this. And we are co-eluding another peak underneath the main peak. And then so we're really seeing a mass fragmentation pattern for two molecules at once. And that can throw off how the computer tries to match that up. Now you can cancel that out. Basically what you do is, when you know this is happening, and you can see usually when it is happening, you can come over to this side and take a mass. You can tell the computer, I want to know what the mass spectra is of this here, and then I want to subtract it from the center, if I take it at the center point here. So I'll take this one and subtract out that one, and then when I run the search, I get a much better hit, because I've subtracted out that impurity. So there's a lot of complexities. The modern software and things that we have and the modern instruments make this really, really nice. I mean, you can really get a good identifications for everything in your solution most of the time, and you can get fairly good percentages. But there is always some error in the percentages, and it only really hurts you the most when we're talking about the minor components. You know, obviously if you have 90% limonene in a sample, and if it's off by 1%, it's not really going to hurt your formulation that much. But if you're you've got a component that's in there at 0.1% and it says it's in there at 0.2, then that could be significant. You know, if it's a very powerful component and you've added it at 0.2 and it's really in there at 0.1, then you've really overblown it, and you know, that's when the perfumer or the flavorist becomes helpful. So what we're going to have is, again, your solution, right? You'll be given your solution, and let's say it has, let's say you had a mixture of essential oils and you had lime oil in there, and you also had say frankincense oil. Okay. These both have alpha pinene. So when you're out, but your alpha pinene is only going to come off in one peak. And that alpha pinene is due from the percentage, let's say it's there at 10%. Some of that alpha pinene's coming from the lime and some's coming from the frankincense. How do we determine how much is from the lime and how much is from the frankincense? Well, what you have to do is you have to know what is unique to frankincense. What components in that oil are unique to frankincense and not in anything else that I think's in this oil. And then that's what I can base what my concentration of frankincense is. So there are things that are unique to frankincense. There's a component called insensyl acetate. It's a minor component. It's a hard one to base it off, but that is one. Even if there's no components unique to frankincense, there may be components in frankincense that aren't in anything else that we think's in our mixture that we can use. Or there may be something in lime oil that we can use to get, like one of the aldehydes that we know is in lime, and none of those are in frankincense. And so this is the kind of game you have to play. And then the more oils that are in there, the more complicated it becomes. But usually one of those oils, like let's say you had patchouli in there, that makes things nice. Because patchouli alcohol is pretty much only in patchouli. And so then once you have the patchouli alcohol, you can set it, oh, I know I got this much patchouli in there, and then all the other components that might be common to something else that are in patchouli, you can scale those down to find out what their contribution to that is, and then figure out what the other things are. So, any questions over this?
Is it a standard program for like the temperature steps and everything that you run for all of them, or do you have to vary that?
Well, we have a set method for essential oils, and we have one that covers everything. It's a long run that's like 140 minutes long, something like that, 120 something. If we know, like if we're running a single oil that we know is a very volatile oil that's light, we have one that's called like EO light, let's say. That's a shorter run that we know everything's going to come off in this turn. But heavier oils, we want a longer run because they got the heavier components, they take longer to come off. And then some of the fragrances have heavy things in them, so we have a fragrance method. But that method is a variable program, a variable temperature method. So it'll go, say, 5 minutes at one temperature, ramp it up at this rate, hold it for so long, go along for so many minutes, ramp it up again, and then finish it out, that kind of thing. And the reason you do that is because sometimes in the middle of the run, let's say, you might have components, if you just kept everything one temperature, you might have some things that co-elude. But if you do this ramping, it increases your separation. Anything else on GC? Okay. Last thing I want to cover then is on your kits and preparing for the exam. Okay. So if you'll notice, I designed this kit. When I went through each group, I tried to give you oils that would not only cover the group we were covering, but also be relevant to groups that we covered later, so that you could go back to those oils when we were in future groups. For example, I gave you, well, the reason I included alpha-pinene is because it's in a lot of different things, but it was used as an example for cypress oil. But you could also smell alpha-pinene if you wanted to in rosemary, white fir, eucalyptus. Those would be the main ones. And then if you went down to the next group there, let's say, well, beta-carotene, let's take the first group again. First group, paracymene, for example. We use that for oregano oil, but we also used carbacrol down there at the bottom for oregano oil, in the, sorry, not the bottom, in the alcohol section. So there's some overlap there. So when I say carbacrol oregano, you can go back up and smell the oregano in the first group, even though I could have used carbacrol in that second group as well. You see what I'm saying? In fact, carbacrol, oregano oil really would have been if I was just looking at main components, that would have been a better one to include in group 2, because that's really what oregano is characterized by, is that carbacrol, the odor of carbacrol. Let's see here. All right, let's take linalool now, for example, in the second group, alcohols. Linalool, I said, is in coriander. And it's the main component in coriander. But look at what else you got. You got lavender down there from the ester group. Sorry, no, lavender's in the ketone group for this one. So the linalool is in the lavender oil at, let's just go over the ones that you have. So for example, linalool, we said was in coriander at what? Say 50 to 70%. I can't get a marker that works now. And it's also in lavender at, say, 30, yeah, let's go 25 to 40%. And I'm not going to ask you to regurgitate these numbers. I'm just trying to give you ideas of what you can do, like when you're smelling linalool. How do you trigger that odor? Well, the coriander would be a good trigger, but smell it in the lavender as well. You know, smell the lavender with the linalool. Smell the coriander with the linalool. Create these memory connections for that chemical that's going to allow you to differentiate it from something else. What else would linalool be in that we have? To a small degree, it's in clary sage, but it's not characteristic of it, so I'm not going to put that in. So then if we go on to geraniol, well, I don't want to do that one. Camphor would be a good one to look at, because it's rosemary, at 30, let's say 30%, up to. And do you have, oh, It can be in eucalyptus, a small amount. It can be in lavender as well. A good lavender, it's probably less than 1%. I would say 1% or less if it's a good. In lavandin, it can be quite high, which could be up to 15%, let's say. You don't have lavandin. We talked about lavandin as a hybrid lavender that's more hardy, more camphoraceous smelling, less floral, but it survives better. Let's see. Oh yeah, the benzoate. No, you didn't. You don't have jasmine, right? Cineol would be a good one to look at. Cineol, because it's in eucalyptus at a 75 to 85%, but it's also in rosemary, and you should smell that in rosemary, definitely. And it's in rosemary at, I'd say 30 to 50%, so pretty significant.
How much camphor is in eucalyptus? I mean, camphor is city also. A lot, I think.
Well, a lot of people do say that, but if you really take some time and evaluate those side by side, the camphor and the cineol, you should notice a pretty significant difference in the way they feel. The camphor in eucalyptus is not huge. Shouldn't be. It maybe, a couple percent, but because you got 85%. Camphor is, I don't know, I'm trying to think of a way to describe the difference. I know what you're saying. They create the same, and that's what they say, a camphoraceous note. The medicinal smell is another term they use, but they really are different. And you may have some trouble at first telling these two apart. Let's see, anethol and estragol, they're going to be different. They were probably difficult for a lot of you as well. Other than those, I don't think I gave too many that were going to be really close in terms of the chemicals. So remember, for the exam, we're only covering the chemicals, okay? And I'm not going to give you any more than 14.
Are we doing two for each category?
Pardon?
We doing two for each category?
That might be a good way to divide them up.
You use the most common from each one.
If, that might be an inclination that someone might want to do. If you're wanting, obviously I want you to take something away that's going to be most useful, and the most common ones are the ones that you really should remember if you want to take anything away from this class. All right, anything else? Any other questions on anything that you've been confused about during the semester that you want to get cleared up before we take this exam next week?
Yeah, you got the power carbon on P1A, I said the word.
Pardon?
Power carbon on line.
On 1,8 cineol. Well, if you look at that structure, the way you have it drawn on your kit can mislead you. But you have to remember these are three-dimensional objects. Your kit shows it like this. Basically. So one might be inclined to believe that this is a chiral atom.
I think that one more above.
Huh?
I think that one was above.
This one up here?
No, there.
This one? That one? Either one of those. You look at it. But look at it. When we go, you have to look at this. There is a plane of symmetry encompassing this whole thing here. I don't know if you can see that. This bisects the molecule right down. If I draw it in this orientation, you might see it better. The orientation that was on the test, I think.
But I think it's drawn this way.
Didn't I draw?
Different way.
Let me see how I drew it on the test. Oh, sorry. I got the oxygen in the back. Sorry. And it's really kind of not as I would prefer it either. What it really should look like more, if we were looking down that, this is symmetrical here. These methyl groups here and here, you could bisect that. There's your oxygen. This comes down. This is down. Got a methyl group off the back. You've got this. There. So now, can you see this plane going right straight through there?
That oxygen might go up. The oxygen didn't.
Huh?
The oxygen didn't.
What's in the center of the plane?
It's in the center of the plane. Now, the oxygen is in the plane of the molecule. With this, I'm making a plane out of this carbon, this oxygen, this carbon, and this carbon are all the same plane. Can you see that everything on either side of that plane is the same? Huh? Which one? This one? This one? That's also in the plane. You have a carbon here with 3 hydrogen on it. Now, how do you make that symmetrical? Like that. So then this carbon and this hydrogen are all, and this are all in the same plane. Remember, this is rotating. So,
I didn't know you split the left one. I didn't know you split those like that.
well, you have to when you're trying to figure out these symmetry issues.
If you look at either of the carbons that you thought was chiral, if you can see coming off them that they have the same group.
Right. If you looked at this group and this group coming off this carbon are exactly the same. They meet at the same point. Okay? And the same thing for this one.
It'd be the same if you had 2 methyl groups or 2 hydrogens coming off, it's the same group.
We got it?
But when you add like another group, if you added another group to that bottom corner, then that would make it.
Another group here?
Yeah.
Yeah, that
Like an O or something.
anything. If you added anything here, then that changes it.
It makes them both chiral.
Then it makes them both chiral. That's right. Yeah.
Yeah. It's a third carbon.
Yeah, well, it would be that one. Yeah. That
But
would-
I gotcha.
yeah.
That was my question in the beginning.
So look for, first of all, when you're doing these, like I said before, anything that's got a double bond on it, eliminate that. It's not going to have it. It's not going to be chiral. Then what you go do is you look for planes of symmetry or axes of symmetry. And then if you can see anything like that, you don't even have to look. You don't even have to look at any of the carbon atoms. If you can see this plane, that solves the problem.
I actually heard him say 0, but I didn't really count the oxygen.
Yeah. So if you can't see a plane, you can't see an axis, and then you got to go through and look at all the atoms that don't have double bonds. Well, what I would do really is go through and look at all the CH2s because you can eliminate the, you know this has got a CH2, that's a CH2. Anything that's got a CH2 you can eliminate. Any carbon that's ending in a methyl group you can eliminate.
What do you mean by that?
They can't be chiral,
Well, yeah.
right? If you've got a methyl
Go
group.
to the next one. If you added something on it, then you'd still have 2 CH2s, but it'd be heavier on that side.
Doesn't matter, but you got 2 hydrogen. Eliminates it. So You know there's 2 hydrogen here, hydrogen, hydrogen. Doesn't matter what else is off of it. Those 2 make it impossible to be chiral. Anything else? No? All right then. We'll see you next week.
Are you going to print those notes from Barry?
The notes from today? Yeah, I will.